Okay, welcome everybody. Today's tech talk will be given by Max von Hippel. Max is an intern at Galois. He's a fifth-year PhD student at Northeastern University, working with advisor Christina Nida Rotaru, and a frequent user of the ACL2 theorem proving system, which is what I studied in graduate school. So I'm very excited about his talk today. He's going to be telling us about his use of ACL2 to prove asymptotic bounds of protocols. So take it away, Max.
Cool. Thank you so much, Ben. I would be giving this in person, but I came down with a cold and decided to spare you all the biomolecular warfare aspect of the talk. So I'm doing remotely from my apartment a few blocks away. So today I'm going to be talking about protocol analysis using real analysis, primarily in ACL2, although I'll also touch on some work done in Ivy. The work I'm presenting comes from two papers, one of which appeared in NETTIES 2023 and the other in the ACL2 workshop 2023. In Union, those have included my collaborators, Pete Manolios, Ken McMillan, my advisor, Christina Nida Rotaru, and also Lenore Zuck. So obviously, I want to thank them all for helping me and mentoring me on these projects. So today I'm going to be talking about transport protocols. And in these protocols, I'll assume that there's a sender and a receiver. The idea is that the sender is going to send packets to the receiver, and the receiver will send acknowledgements, which cumulatively acknowledge those packets. So for example, if I send a packet with sequence number 13, let's say, and then subsequently I receive an acknowledgement with number 14, that acknowledges not just the packet I just sent, but all the previous ones. So you can think of an acknowledgement as almost being like a what I would like next number, because it's the lowest integer such that the receiver has not yet received a sequence number or a packet with that sequence number. The round trip time in a transport protocol is going to be the time between when a packet is transmitted and when the sender first receives some confirmation that the packet was successfully delivered. So it measures how long it takes for the sender to know that it successfully transmitted some information. And that knowledge will happen because of an acknowledgement. And I'm going to go over in a moment what that looks like in real life. Importantly, these round trip times are useful because they give us some insight into the congestive state of a network. And that insight can be used to change the pace at which the sender will transmit data so that it doesn't overwhelm the network, but it also doesn't underutilize the network. And among other things, one aspect of the decision-making process that goes into that is the retransmission timeout, or RTO, which is the amount of time the sender is willing to wait for a new acknowledgement before it decides, you know what, I think that something went wrong, the receiver isn't trying to send me anything, or it's all getting lost. I need to go back and retransmit some data because I don't think that there's an ACK that's going to arrive anytime soon. That RTO is computed using round trip time measurements. So the sender will measure a bunch of round trip times and then compute a number called an RTO. And as a result, the dynamics of the sender will change over time depending on the dynamics of the network and how long it takes for messages to propagate. So why do we care about these detailed acronyms I just introduced? Well, one reason to care is because an RFC tells us we should care. So RFC 6298 reads the internet to a considerable degree relies on the correct implementation of the RTO algorithm in order to preserve network stability and avoid congestion collapse. What is congestion collapse? It's a scenario in which the congestive dynamics of the network sort of spiral out of control, and suddenly it's impossible to get new data to progress through the network. So if the RTO is too low, then there will be unnecessary timeouts because of just small delay variations with the delivery of acknowledgements, which could open up the protocol to denial of service attacks. On the other hand, if it's too high, there will be an overuse of resources by the sender because when congestion occurs, the sender will wait too long to respond to that congestion and send retransmit packets. So it's important that it's neither too low nor too high, but what does that mean exactly? That's something we study, and no prior works had formally verified either Karn's algorithm, which is the way that the round trip time is measured, or the retransmission timeout computation, which takes the round trip time and computes an RTO, which is the time we'll wait to timeout. So unsurprisingly, that's what with my collaborators I did. Okay, so one of the first things that you learn when studying this problem is that the round trip time is pretty hard to define and hard to pin down. And it seems very simple at first. It's like, yes, the time between when I send something, when I receive an ACK, but I'm about to show you why it's really not that simple. So imagine the following scenario. We have a sender and a receiver, and in the first time step, the sender is going to send a packet with sequence number 1 to the receiver. So the receiver, once it receives it, knows that it has received packet 1. The receiver responds with an acknowledgement of 2, which cumulatively acknowledges the packet of 1, which the sender receives. So the sender gets gets the acknowledgement. At this point, the sender can measure a round trip time of 2 minus 1 is 1. So the sender's local time when it sent the packet 1 was 1. When it received the acknowledgement 2 is 2. 2 minus 1 is 1. Unambiguous, clear round trip time. This is like the classic example. It's how we would imagine that the network would work in general. But unfortunately, it's not how things always work. So subsequently, suppose that the sender transmits the next packet 2, and this packet gets lost in transit. Sender has no way of knowing that the packet was lost, other than that it doesn't get an acknowledgement soon afterward. So next, the sender goes ahead and transmits another packet, this one 3, and now the receiver has received 1 and 3, but not 2 because 2 is lost. So the receiver responds with a cumulative acknowledgement of 2. Importantly, acknowledgements are cumulative, so the receiver cannot acknowledge the packet 2 because it didn't get it yet. Therefore, the smallest integer satisfying the property that the receiver has not received that number yet is 2. So that's the acknowledgement that the receiver sends. And once the sender gets that ACK, it knows that that 2 never made it through. Because had 2 been transmitted, then the ACK would have been at least 3, if not 4. So because the acknowledgement doesn't ACK anything new, the sender is able to derive that it needs to retransmit the packet 2. It does so, and subsequently it received an acknowledgement of 4, indicating that the packets 1, 2, and 3 have all been successfully transmitted. So what is our new round trip time upon getting the acknowledgement of 4? Well, one possibility is 7 minus 6 equals 1, because we could measure the time between when the sender retransmitted 2 and when it received the acknowledgement of 4. And if the sender knows that the original transmission was lost, this would be a well-defined operation. It makes sense. But from the sender's perspective, it's entirely possible that actually the retransmission was lost and the original transmission was delayed. And in that case, the correct round trip time would be 7 minus 3 equals 4. So the sender doesn't have access to enough information about the global state and cannot have access to that information to be able to derive the true round trip time, which means that measuring round trip times from the sender's perspective is an underspecified problem. It doesn't have enough information to do so unambiguously. The solution, which Karn and Partridge suggested, but which they both refer to as Karn's algorithm, is as follows. First of all, we can refer to the first stack I showed as being unambiguous because it was quite clear which packet it was acknowledging. There's no retransmission. We can refer to the next one as being a duplicate because it had value 2 and we'd already gotten an acknowledgement of 2. And the last one was neither a duplicate nor ambiguous. And so that's essentially the rule, which is that we will only compute, sorry, the other way around. The last one is ambiguous, but not a duplicate. So the rule is we will only compute RTTs if we get an unambiguous new ACK, an unambiguous non-duplicate ACK. So the second ACK doesn't count because it's a duplicate. The third ACK doesn't count because it's ambiguous. So we modeled this system in Ivy, which is an interactive verifier for inductive invariance, and proved some theorems. The most important of which, first of all, were a number of inductive invariants about the algorithm's variables that showed that they essentially work the way you'd expect them to. But then also that Karn's algorithm really does measure a round trip time, and it measures a pessimistic one, meaning that if it measures a round trip time for one of the packets in a sequence of packets that get sent for which there's a single acknowledgement, that round trip time will be the worst of all the round trip times for that sequence of packets. So essentially the round trip times you get from Karn's algorithm kind of in some sense give you an instantaneous lower bound. However, there are downsides to Karn's algorithm, like the fact that since it doesn't sample all the time, you could potentially have an outdated RTT value if there's a lot of acknowledgement reordering and retransmissions. After having formalized improvements and properties about the RTT, we then wanted to look at the RTO. So just to remind you, the RTO takes as input these RTT measurements, and then it computes the timeout value that we're going to be willing to wait. So the problem we wanted to ask was if the samples that we compute with Karn's algorithm of the round trip time for packets are bounded, then can we prove anything useful about the retransmission timeout, which is computed over those RTTs? And we ran into, yeah, go ahead.
Can I ask a question about this Karn's algorithm thing? Because it seems like we're moving on.
Yeah.
So that I'm a little confused about this property that it's pessimistic. And I guess and maybe it's about the semantics of what exactly the property is. But I'm imagining a network where, like, I don't know, half of my packets get sent and received pretty quickly or whatever. So RTT of 1, and half of them get delayed like 4 seconds or whatever. And so they're like always delayed, and I always end up throwing them out. It sounds like this algorithm would tell me that the round trip time for my network is 1, which doesn't sound pessimistic because some packets definitely have a slower round trip time.
Are you imagining that you send the fast packets and then you send the slow packets and then you get the first new unambiguous acknowledgement?
I hadn't got that far to imagine like any specific ordering of them or something. But like, I guess it seems like you're only counting the packets that like have the happy path. And I could have, maybe it feels like I could have a session where, you know, there's a lot of packets that consistently get this like slow path, but they always are like act in weird ways because they're slow.
Yeah, so there's kind of 2 parts to your question. So one is in a narrow sense, when we receive a new acknowledgement, a new unambiguous acknowledgement, it can acknowledge multiple packets for the first time. So for example, if I've transmitted like 3, 4, and 5, and the highest ACK I've received is 3, and then I receive an ACK of 6, well, 6 newly acknowledges 3, 4, and 5, right? So, so in that narrow sense, it is true that the round trip time I'll measure will be the time between when I started sending those packets 3, 4, and 5, and when I got that ACK. And that's going to be at least as big as the time between when I sent 4 and I got the ACK and the time when I sent 5 and got that ACK. So that's essentially where the pessimism comes from, is that the acknowledgement acknowledges, you could call it like a window of packets. And it's the largest RTT of anything in that window, if you define RTT as the time in between when I transmitted and when I received any acknowledgement that acknowledges the packet for the first time. But the other aspect of the problem is that you're absolutely right that if you have a network where like funky bad things happen and then the network behaves really well, and then funky bad things happen and the network behaves really well, and you take RTT samples, you could end up in a scenario where you only measure good RTT samples, because when the funky bad things happen, the acknowledgements are ambiguous because of retransmissions. And so the only guarantee is that over the window of packets that are newly acknowledged, the round trip time you measure is pessimistic, but there's no guarantee whatsoever that it's pessimistic for all the packets that were transmitted since the last sample.
Okay, and I think that's the subtlety I was curious about.
Yeah.
Thanks.
Yeah, it's a really interesting question. And this is something I'm actually continuing to study in current work, and like is not widely observed in literature I've read. So great point. Okay, so we studied the RTTs, and then we wanted to use them to study this other mechanism called the RTO. And both Karn's algorithm and the RTO computation are sort of like Lego blocks that appear in a lot of other protocols. So there's a number of transport protocols other than TCP that use these components, or use just one of them, or use both, or use like some slightly modified version. For example, like Quick uses a slightly modified version of the RTO, but does not need to use Karn's algorithm because it has a new sequence number for every single packet. Whereas a retransmission in TCP would have the same sequence number as the original transmission. So these components are broadly applicable. I was mostly interested in how they interact, but they're also like independently interesting for a lot of different protocols. And trying to study the RTO, I ran into an unexpected hurdle, which is showing this incredibly simple theorem that if A is a number between 0 and 1, but less than 1, then the limit as n goes to infinity of a to the n is 0. So I'm going to spend some time talking about that theorem and how it can be solved in ACL2 in sort of a deep dive. And then I'll zoom out at the end and give a little bit of broader context about what we showed about the RTO. So just to start with, I should give the definition of what a limit is, because not everybody maybe remembers this or knows it. So the way we define a limit in mathematics is with what's called an epsilon delta proof. So in this case, I'm imagining that I have a function f over some domain x, and it has a limit as x goes to infinity of L for some value L. What that means technically is that there's like an evil gremlin who hates me, and this evil gremlin is going to give me values called epsilons that are greater than 0. And is going to say, mwahaha, I hate you, Max. You need to prove to me that it gets at least epsilon close and then stays that close forever to the limit. And then I am responsible for coming up with some delta where I can say, look, if x is greater than delta, then f of x is definitely within epsilon of L. So this is sort of like an interactive problem. And if you do it all purely symbolically, then you've constructed a function that outputs your delta, and you have like a reliable witness no matter what epsilon is, and that's your proof. In ACL2, this takes kind of an interesting form because ACL2 is a first order logic. And so in order to do this, you need to do some trickery with skolomization to introduce quantifiers. So ACL2 has some limited support for second order logic, but it's entirely manual and is based off skolomization. And this is kind of what it looks like. So essentially you define what it would mean for the limit to hold in terms of a quantifier. In this case, I'm saying that what it would mean would be that there exists some x and e. So sorry, what it would mean is that for x and e, both positive rationals, there exists some delta, also a positive rational, such that if delta is less than x, then the distance from f of x to the limit is less than epsilon. And then having defined what it would mean for the limit to hold, then I have to prove that it holds. And I do so by providing a function that produces my delta, which essentially witnesses the limit. So that's sort of a nitty-gritty detail about how you do this in ACL2. There's another approach in ACL2 called non-standard analysis, which I didn't do, but is super cool. So if people want to chat about that, I'm happy to talk about it more. So I formalized this proof using a proof sketch that Ken McMillan came up with for the original NetEase publication. And it was pretty difficult. And then afterward, I thought, there must be an easier way to do this proof. So I sort of revisited it, got some help from Pete, and Pete came up with another proof sketch, which I formalized, which was much, much simpler. And actually some people in the Math Fun channel here at Galois have come up with another proof, which I have not formalized yet, but would like to based off the Archimedean principle. I'll be going over those proofs in addition to the really obvious one and showing you why essentially the obvious strategy won't work for me in ACL2. So this thing seems incredibly easy, but it turns out like many things, it's just not that easy in the theorem prover, and I'll show you why. So the obvious way that we would prove this theorem on paper is I would say, let delta be logarithm base a of epsilon. In that case, if n exceeds delta, then I can exponent both sides, and I can get a to the n is less than a to the log base a of epsilon, which is epsilon, and I'm done. This is like the most straightforward proof in the world, and all you need to be able to, to have in order to do this proof is access to an arbitrary base logarithm. There's a variant of ACL2 called ACL2R made by Ruben Gamboa, which supports a theory of real numbers. It's not the commonly used variant, but it is interesting, and it's useful for real numbers. And the obvious proof I just gave, I formalized also in ACL2R. It's more or less exactly what I showed. The only difference is that ACL2R does not support arbitrary exponent or arbitrary logarithm. So I have to do some change of base trickery in order to make it work. And the one trick that I did not think of until it was pointed out to me, and then I felt like a real doofus, was that I can take a to the n by doing n times ln of a. So, e to the n ln of a is the same as e to the ln of a to the n. So if I take that trick and I do the standard change of base formula, I can do the sort of obvious proof. Unfortunately, my work. Unfortunately, my work on this was in the context of a broader model that was pretty elaborate, which I'd already built in proper ACL2. And the two theories are incompatible and have slightly different features. So it was not tenable for me to just take my existing work and port it over to ACL2R to prove the theorems I wanted to do, which meant I needed to have a way to do this in ACL2 proper. Unfortunately, ACL2 does not support real numbers. It supports rational numbers. So more precisely, it doesn't support irrationals. And the logarithm of a rational might be irrational, which means that the proof you're seeing on the screen right now cannot be written down in ACL2. So after a lot of anguish, we managed to formalize some rational proofs in which we don't rely on the logarithm. And these proofs go through an ACL2 proper and allow us to study the RTO system. The first one, which Ken McMillan came up with, is the one that we use for the Netties paper. And I find it quite confusing. I'm really impressed Ken was able to come up with it. And I do not have any good intuition for it. The basic premise is we prove these three lemmas. The first is that if I have a fraction inside of a ceiling, I can sort of decompose it into an inner fraction inside of a ceiling and an outer denominator or numerator. Anyway, an outer fraction outside of a ceiling. The second is that for this identity k equals ceiling of a over 1 minus a, I can rearrange things and get a is less than or equal to k over 1 plus k. And the third is that for this function, f sub a of n equals k a to the k over n, I can prove an inductive theorem that for all n greater than k, a to the n is less than or equal to f sub a of n. Once I've proven these three theorems, which is totally non-trivial in ACL2, and I think took over 100 lines of just raw proof without any automation, then I'm able to come up with a value d, able to the ceiling of k to the k over epsilon, let delta equal the maximum of k and d, and my proof follows. Even the proof itself doesn't follow immediately. It requires some additional machinery. And formalizing all this was exactly the nightmare that you think it is looking at the slide. It also doesn't really give any insight about, I guess, the nature of the limit. And I think aesthetically as a mathematician, I like the idea of my proofs explaining something to me other than just the end result. So the alternative, which Pete came up with later on for the workshop paper, is a much simpler proof that relies on the binomial theorem. In this case, I'm going to say epsilon and a are both rational numbers. So let's say epsilon equals x over y and a equals p over q. These are just new variables I've come up with for the normal form of the rationals. And I'm going to come up with a new value, b, which is going to be p over p plus 1. So first of all, I can prove that a is less than or equal to b. This statement is very intuitive. It's essentially like saying that 3/4 is greater than or equal to 1/4, for example. So that's a very intuitive statement. And then the real trickery is that we take this number b and raise it to the power of p, and the top becomes p to the p and the bottom becomes p plus 1 to the p. And by the binomial theorem, the bottom expands to a bunch of stuff plus two terms that are p to the p. So one of them is at the beginning, and the other one is p times p to the p minus 1, which is p to the p. So essentially we get p to the p over some stuff plus 2p to the p, which is less than or equal to 1/2. And at that point, we're off to the races because it's very, very easy to prove that if I have a number that's less than 1/2, that as n goes to infinity, that number raised to the n goes to 0. That goes through very quickly in ACL2 with very little work. So the theorem pretty much immediately follows. So putting this all into context, I'll remind you that the RTT was the time between when we send a packet and when we get some confirmation that the packet was delivered. And we measure RTT samples using Karn's algorithm, and then we use those to compute this retransmission timeout. And if more than that much time passes without new acts, the sender backs off and retransmits unacknowledged packets. So we ask the question, what happens when the samples are bounded, which leads us to these proofs I just showed. The actual computation of the RTO looks like this. First of all, we have two variables, a and b, or alpha and beta, that are both in 0 to 1, but less than 1, and some other constant g greater than 0. The RTO uses two internal variables. One is the SRTT, or smoothed RTT, which is a rolling average of RTT values. And it's essentially the prior smoothed RTT plus this alpha times the most recent RTT sample. So it's just a smoothed rolling average of the samples. The idea of the SRTT is to kind of accommodate for small jitter and not take into account when we compute our RTO. Next, we have the RTT var, which they describe in the RFC as being an RTT variance. It's quite easy to prove using the ACL2S counterexample generator that this is not a statistical variance. But as we'll show in a few slides, it does capture some notion of variance. And this is, once again, a smoothed average, but this time between the previous RTT variance and the delta between the previous smoothed RTT and the actual sample value. And then finally, the RTO is computed as a smoothed RTT estimate plus a maximum of either this constant G or 4 times the variance. So when we look at these, we notice that both internal variables, SRTT and RTT var, have kind of the same shape, which is 1 minus some constant, for that constant being between 0 and 1, but less than 1, times the prior state, plus that constant times something that maybe I could bound. And so maybe I can kind of zoom out for a moment and study that shape, and then zoom back in and look at the equations. So here's that shape written again. I have the next state equals 1 minus some constant times the prior state, plus that constant times something I've bounded. And if I unfold this over and over, I'm going to see a pattern, which is that I essentially have to deal with the initial term, 1 minus constant to the number of unfoldings times the initial term, plus, in parentheses, this function of the constant plus 1 times the bounds. And the important thing is, let's say that I have infinitely many samples that are bounded. Well, then this I is going to go to infinity. I'll be able to unfold an infinite number of times. And the limit of all of this stuff is going to go to 0 because of that theorem we just proved that says that if a fraction is between 0 and 1 but less than 1, then the limit of that fraction raised to essentially the infinite amount is 0, which leaves us with just 1 times the bound. So with interval arithmetic, we derive that the limit of the system is the bounds. So we apply this to the SRTT and RTT var in the context of bounded samples. And just to illustrate what we prove, I'm going to show a case of uniform distribution of samples between 60 and 75, but this is totally arbitrary. We prove everything in the theorem prover, and it holds for any distribution as long as there's bounds. So suppose the samples are bounded. In this case, we prove, first of all, that this SRTT, which is a smoothed estimate of the RTT, is also bounded. And moreover, its bounds are going to converge the sample bounds. And you can see in the example, I've drawn the lower bound on the SRTT in orange and the upper bound in blue. And those bounds converge very quickly to 60 and 75, which are the bounds that I chose for the samples. The next thing we show is that the RTT var has an upper bound. And this upper bound converges to the diameter of the bounds on the samples. So in other words, the distance from 60 to 75 is 15. And the minimum sample is 60 and the maximum sample is 75. So the diameter is 15. And indeed, we see that the RTT variance has an upper bound, which converges to 15, which tells us that it does measure something that is at most some notion of how far the samples could vary, because the most they could vary is the distance between the lower bound and the upper bound. Nevertheless, we're able to show that even when the samples are bounded, it's possible for infinitely many timeouts to occur. So recall, a timeout occurs when the retransmission timeout is less than the sample value, because in that case, we wouldn't even measure the sample because it took too long for it to arrive. And we can come up with pathological scenarios very easily in which a timeout occurs and the system returns to exactly the state it was in before the timeout, implying a cycle where infinitely many timeouts. And one such scenario is illustrated here, which is where every 100th sample is the maximum and everything else is the minimum. And that causes infinitely many timeouts. So what that really means in the context of the internet is we can't rely on the internet to not time out, to not have the sender timeout and retransmit, even when we have bounds on the speed at which information is propagating, which I think is interesting and maybe not what was intended. In theory, you would like to have a system that adjusts to the bounds by learning them over time and then stays fairly stable within those bounds, but that does not seem to be the case. So proving all this was quite tedious in ACL2, in particular proving Ken's theorem was pretty difficult, and led me to have some thoughts about how ACL2 could be improved. First of all, when I did the obvious proof in ACL2R, it was interesting to me that some really basic arithmetic machinery was missing from the prover. Things like having the arbitrary base logarithm or the arbitrary exponent, and these are things we use all the time. And so ACL2R is, there are people who use it, but it's mostly a niche research community that use it. Like Ruben Gamboa, who made it, uses it a lot. But I feel that sometimes these types of tools can be dominated by the people who are super duper expert in them, and then they maybe don't add like the functionality that's useful for novices. And in my opinion, there's some low-hanging fruit that would make ACL2R more useful, more easily useful for students and people who are new to the platform. Another thing that was interesting to me was I had really, really good, like detailed, interesting reviews. And one of the things that the reviewers pointed out was places where I had proven lemmas that were already proven in the ACL2 books. So a property of ACL2 as a theorem prover is it comes with all these books that get certified when you compile the prover. And so you can import any theorem from those books. And the problem was it was really hard to find those theorems. So the ACL2 code tends to be untyped. I write typed code, but most people don't. And a lot of it doesn't have that many comments in it. And it can be pretty difficult to find a theorem that does what you want. So searchability could be improved. And especially in light of the IRAD work I've been doing here at Galois, I personally really feel that a large language model could be used to make the book super searchable, and it would really help. The easiest proof for me to write and understand by far was the binomial argument. And I don't know about you, but I find it a lot more rewarding when I can write a proof that I not only understand, but also like provide some insight into why the thing is true. I'd also like to try doing this proof that was suggested in the Math Fun channel based off the Archimedean principle, but I haven't had a chance to do that yet. Finally, and maybe most interestingly, it would be really cool to have some sort of bridge between ACL2R, which supports irrationals and addition irrationals, and ACL2. So I've been in talks with Pete Manolios and Matt Kaufman about this, and Matt Kaufman's a co-author of ACL2. And what we've been talking about is that in theory, if you have a theorem in which all the variables are typed as rationals, and you have a proof of that theorem that uses a theory of reals, it seems intuitive that that theorem should be able to be imported into an environment in which all proofs need to be written in rationals under the justification that essentially what's true in the rationals is true in the reals. The kind of hang up, I think, is that in ACL2 proper, real is a shorthand for rational, which can cause some funky things. Like, for example, in ACL2, you can prove that there's no, in air quotes, real number equal to the square root of 2. Of course, there is one, and you can find it in ACL2R. And so you would need to have a strong typing system for this bridge that would make sure that all the variables in the theorem are proven in ACL2R to be rationals. So this is sort of an interesting model theoretic problem. And I don't know that it'll be solved, but I think it's kind of fascinating and would be a fun paper to write. And with that, I'll take any questions.
Max,
Oh, sorry, go ahead.
okay, I'll go first. So I have some experience doing inequality proofs in ACL2, and not ACL2 to R, just ACL2. And I found that there were some things that were sort of automated, and it was hard, but it was very hard to do like long strings of inequality chains with anything other than a manual approach. And I was wondering what your experience was doing those kinds of like kind of finicky like algebraic proofs, and if you've used any other provers or other formal methods approaches, if other systems had better or worse kind of infrastructure around doing those kinds of finicky chains of inequalities.
Yeah, that's a really good question. I very much had the same experience. I audited Adam Chapala's class at MIT on Coq, and Adam's approach to verifying things in Coq involves writing these incredibly smart kind of hammer tactics that can do 100 million clever things and are sort of heuristic in nature, but tend to do really well. My experience doing his homeworks was that when I was doing these types of proofs, I often could kind of prove the relevant facts that were convincing enough for me to believe that the thing would be true, and then just call one of his tactics. Like he has one called linear arithmetic. That's not actually linear arithmetic. It's like linear arithmetic plus a million incredibly clever things that he invented. And it would take care of the rest for me automatically, be done. So that's not the case in ACL2. I think that like if Pete Manolios was here, he would probably say that it's totally possible to write stuff like that ACL2. The downside would be that that may be kind of folklore knowledge that very few people have, right? And so there's a degree to which if you're advised by or working with the right person, you can figure it out. But if you're on your own, you may be out of luck. By the way, the Ivy work is kind of like that too, in the sense that Ivy is pretty finicky and there are some tricks to how you use it. And I was working with Ken McMillan, who made Ivy. And so there were multiple times where something wouldn't work and I would email Ken and he would update Ivy and then it would work. And you know, sometimes with these FM tools, they're like incredibly powerful, but they don't really do what you need them to do unless you literally have access to the person who made them, who understands how to use them.
All right, cool. Thank
I have a very basic question as somebody who knows almost nothing about ACL2, but why is there a schism between ACL2 and ACL2R? Why,
Yeah.
why was it not conceived to just make ACL2R part of ACL2?
Yeah, that's a really good question. I think it should be. ACL2R just obviously offers functionality that's useful, and I really see no reason why it's not. I think that, so historically, ACL2R was invented after ACL2. ACL2 is a very old theorem prover. It's sort of weird because it's like, it's niche in the sense that not a lot of people use it, but it comes from NQThem, which was like one of the foundational original theorem provers from Boyer and Moore. And kind of the modern technology of theorem proving to a large extent comes out of that tradition. So ACL2 has its place in the history of theorem provers, yet nevertheless is today less popular than something like Lean or Coq. But it's quite old, and the fact that it's old matters because it means that there's a whole bunch of code that's been built up. And if you want to change something foundational, you have to like refactor a lot of that code. And so adding ACL2R would break a bunch of community books, which would mean that not only would you need to have buy-in from the community, you would also need to have some grad student like who knows enough about ACL2 to fix all the books, but also has some reason to be interested in doing so and the time to do it. And my experience has been, and I wonder if Ben's experience is the same, that by the time you get to the point where you actually understand the system well enough to make a contribution like that, you're pretty close to graduating. And you know, you really just want to wrap everything up. So like, for example, I would love to work on this problem of making a bridge from ACL2R to ACL2. I think it'd be incredibly useful. You know, it would basically solve the problem without needing to refactor all of ACL2. But I would even more love to finish the PhD and move on with my life. And so there's that very practical limitation of you know, just like who's going to write the code.
Any other questions? Nope. David Holland.
I'll have one if nobody else wants to go. And that is, I was wondering, what is the approach, and this is possibly a long topic that is going to require multiple digressions and best discussed elsewhere, but what is the approach of ACL2R to the problem that when you sit down and try to axiomatize the reals, you end up being able to prove false?
Yeah, ACL2R uses a theory of non-standard analysis, and I don't know the details of it. It's all written up in Ruben Gamboa's dissertation. The people at the ACL2 workshop thought it was quite funny the way I wrote my proof, because I did an epsilon delta proof, and in non-standard analysis, I guess there's a totally different way to prove limits that is available to you. That's much easier. I think that you can just prove that the fraction decreases, and that's somehow sufficient. I don't remember exactly why, but regardless, I joked that to me, ACL2R is ACL2 logarithm, because I just used it because I had access to a logarithm, and I didn't have access to it in standard ACL2. Yeah, ACL2R uses some non-standard theory of analysis. And what I remember about it is that it involves non-standard numbers. So there's a number that's less than all real numbers. There's a number that's greater than all real numbers. So you can kind of construct some things that are not part of the standard theory of the reals, and hence why you can have a consistent theory, I guess. But unfortunately, I don't know how the foundational model works in detail. I'd love to though. It sounds fun.
All right.
I have another question for you, Max, which is, have you shared these results with folks from like the network community or like standards organizations or anything? Like, as you said, that sort of possibility of infinite timeouts, even in a like steady state network, seems like undesirable. Like, have you chatted with networking people and did they go, oh, this is just some weird corner case? Or did they go, maybe we should fix this? Or
Yeah, a little bit. So I wrote a blog post for the RIPE blog, which is RIPE is this organization that it's a big internet provider or a big ISP. I also wrote a blog post. Well, I published the same blog post in both RIPE and AppNIC. So those are two ISPs that cover a significant portion of the world. I think AppNIC is like most of Southeast Asia. And those blogs are technical blogs that have, I mean, academics read them, but I think they also have a wide readership among just kind of networking professionals. I've written blog posts a couple times for those venues, and mine are definitely a little more theory driven than the average. Like it's more kind of measurement studies and stuff like that. What I'm working on now is a formal analysis of go back N, building on the work I presented today. And go back N is essentially the foundation of the sliding window protocol in TCP. And I think that probably once I've extended this to go back N, it'll be a little more interesting to people because the components I've studied are so foundational that you have to do a few logical leaps to think about how this actually impacts something at the level of like quick, right? And so as I kind of work my way up the stack a little bit of kind of increasingly large components of commonly used protocols, then the import becomes more obvious. So I think that's essentially the answer. Also, in terms of sharing results, it's useful to point out that all my results are part of the ACL2 books now, which means that anytime somebody updates ACL2, their update will not be accepted unless all my results certify. So the replicability of the work is now baked into the ACL2 theorem prover, as long as it exists, which is kind of cool.
So, Max, you said something interesting that like your a lot of the things you were trying to prove were kind of already proved in a different form than the ACL2 books. And like the problem, but there was like theorem matching or something like that. Is it just that you're using, I mean, I can see that maybe that's kind of a hard problem because the types in your proof might be different from the types that the ACL2 book uses. And they might, you might have like a different statement of the theorem, but they might be morally equivalent, and that equivalence might be itself like a theorem that's difficult to prove. I feel like that's a really interesting, it's sort of pretty common that you find that something has already been proved in a different form. Even like the function you're using is already exists. And Haskell has this Hugel tool that helps you find things at least that have the same type as the thing you're looking for. What are your thoughts on that? Like what would be a useful tool so that we don't just kind of constantly replicate work, I suppose is the question.
So we get to a fundamental rift in the ACL2 community, a drama, one might say, which is that many people who use ACL2 don't believe in having a typed language and think that types are unnecessary cruft and that you should simply write predicates for everything. They are what you might call the old school contingent of the ACL2 community. And ACL2 does not have it's not a typed language. You can write predicates to check if something is of a certain type, but it's not a typed language. So I use ACL2S, which is a variant of ACL2 built largely by Pete Manolios, although many people contribute to it. And ACL2S is ACL2, but with types. So you have type annotations on everything. And I will say that if everybody else used ACL2S, it would have been considerably easier for me to find the theorems I was looking for because I could have done more elaborate greps on the types of the functions I expected to exist. However, it's often the case when you read a proof in vanilla ACL2 that you'll find something in which the theorem statement is given at a high level in English and a comment at the top. And then there's a whole bunch of essentially unreadable Lisp below that has no type annotations and no comments. And then at the end, there will be a QED. And unless you really, really know the domain extremely well, or like many ACL2 practitioners have been using the theorem prover for 30 years, you'll look at that and not have any idea what you're looking at. So I feel that the thing that would help the most is increase the adoption of ACL2S. And I'll say that a lot of people who are my age who are picking up ACL2S for their graduate research are choosing it for that reason, because it's just easier to read your own code, to read other people's code, et cetera. Now, as far as large language models are concerned, I would love to be able to describe in English more or less the theorem I'm interested in, and have a large language model generate, say, a bunch of grep patterns that it thinks might match potential formalizations, and then search for those, right? That would be exceedingly useful for me. I think it would be easier if people had types, which most ACL2 users do not use.
Right, and I can imagine that even if it's typed, you still have like potentially a gap, because your representation of the problem might be different. So it doesn't like totally solve it, but it makes total sense that it's like your type is a kind of, theorem specification in a sense. It's like if your things have like the same types, then there's, or at least the same type structure, you have at least some hope of finding the thing that you're trying to prove. Whereas otherwise, it's just like you say, a big pile of nonsense with some English kind of description.
Yeah, exactly. That is exactly the case. Also, the types in ACL2S have the rather interesting property that they are inherently enumerable, which means that anytime you define a type, you immediately have a fuzzer for that type. And then you can write down a property that's like an ansatz that you're not really sure about, and you can write proofs nil testing true, and it will fuzz your property. And that fuzzer will do intelligent things based off the shape of the property with the theorem prover in order to increase the odds that it makes it past the hypotheses in the property, so it's non-trivial. The more theorems you have, if they're good theorems, the better it'll do at that. And so if everybody was doing typed work, I could find a bunch of really juicy theorems about the system I'm interested in and import them, and then have a better enumerator to generate counterexamples. Modulo some details about like improvements being made to the enumerator and stuff like that.
Yeah, it makes me wonder whether, I don't know whether it's sort of related to all the quick chick work that Benjamin Pierce and Leo Lampropoulos have been doing, I suppose. Yeah.
Also, Jasmine Blanchett, I think, has done some really exciting work about counterexample generation, I think in Isabel. Counterexample generation is one of my favorite topics, and there's a bunch of very cool papers at Popple and Cav on this type of thing.
Yeah, very interesting. Yeah, thanks, Max. I guess that's it.
Cool. Well, thank you very much.
Thanks, Max.